Okay, so good morning to the fifth lecture in general for the CFD course. And today we essentially continue with the material that we started yesterday. Namely, we will look at different types of equations, different types of differential equations, and study in a little detail the properties of the various solutions. But I would like to start with a short summary of what we did last time. So that's yesterday afternoon. We started to look at the concept of well-posedness of differential equations, and we realized that in the end it's three different properties that are important for well-posedness, namely that there is a solution, as a solution exists, that it needs to be unique, and it needs to be dependent in a straightforward way to the boundary conditions. As soon as you have a well-posed problem, then you can actually come with numerical methods and solve for that solution. If it's not well-posed, so if it's ill-posed, then typically you would need to have additional stabilization or regularization methods for the solution to work. Examples are inverse problems, for instance, problems when, for instance, you have given the solution, but you would like to find the initial condition. And the problem there is that this is typically not a unique problem. So you need to add some, well, stabilization in one way or another to converge to a good solution. We have then continued with looking at type classification of differential equations. And we did a short derivation using this two-dimensional space and the specific curve in this two-dimensional space. And then we could realize that we can calculate eigenvalues of the involved operators. And then we can, depend on the eigenvalue, we can find out whether an equation is elliptic, parabolic, and hyperbolic. And then we also started to look at the first type, and that was the elliptic type, where we saw that the Poisson or the Laplace equation is a typical exponent of elliptic equations, and we could also see what properties that these solutions have. In particular, that boundary conditions need to be given all around the domain, which also means that we need to solve the whole domain at once with appropriate numerical. So this is what we discussed last time, yesterday. So are there any questions or something that we should discuss a little bit more? If not, then we continue with today's content. And what we do today is we will look at the hyperbolic problems and parabolic problems, so to conclude our exposition of the different methods. And then in the second part, we will start to look at finite difference schemes. And we learn a little bit about how finite difference schemes work, both in space and in time. So that's today's plan. Okay, but then let's start with hyperbolic problems. So typical examples of hyperbolic problems are essentially problems where you have advection processes. So you have a quantity that moves in both space and time. And what you can think of here is, for instance, a wave equation, where everything is transported in a wave-like form. The advection equation, which we will look at in much more detail later on. And on a bigger scale, for instance, also the compressible Navier-Stokes equations. Navier-Stokes equations, they are also part of the class of hyperbolic problems. Here it's important to see that this is for the transient, so the time-dependent compressible Navier-Stokes equation. When it comes to the physical processes, as I was just saying, we look at advection processes. So some quantity is moving in space and time. Typically, that would mean that there is a wave-like character of the solution. So it moves as a wave, not as a diffusion process, but rather as a wave. And it's important that for a truly hyperbolic problem, there should be no dissipation involved. So without dissipation, so that means an undamped advection process. As soon as you have significant amounts of dissipation, then you would more and more depart from the hyperbolic character of the equation. But let's just start now with a simple example of that, and we take the usual example, and that is the linear advection equation. Linear advection equation, that's also called the advection equation. And if I write it down, it's du dt plus a times du dx being 0. This here is the advection equation. Now, the question is, can we find an easy solution to this equation that would directly kind of help us understand how we could interpret the results of this? And in principle, we can just do the same steps as we did yesterday with this curve in space and time. Just instead of having x and y, we would now look at it in x and t, but the rest is the same. So what we do is we calculate the total derivative of u with respect to t along a specific curve f, which we'll calculate afterwards. And what this then gives is du dt plus dx dt along the curve f times du dx. That's exactly the same way as we did yesterday. And then this guy here we can call lambda. So in a sense, the eigenvalue that we introduced yesterday. Okay, but now you see, in fact, that these two equations that I wrote down are not very different. So I mean, you have this term that's the same, you have this term that's the same, you have kind of this a that looks a little bit like this. So what you can do now is you can actually combine these two equations together. So what you would then get as a result is du dt along the curve f is lambda minus c times du dx. So what we have now done is we have removed the du dt from this equation. Okay. So the next step now to realize is that if we have written everything like this, so if we choose now lambda to be dx dt along the curve f, as we have indicated here, yeah, what happens then to the solution of the problem? Well, what we get is that du dt along the curve f is in fact going to be this should be a, of course. So the solution should be or the change of u along t is actually going to be 0, because because essentially this term then will disappear with lambda being a. So if we do that, then this equation here will become 0. So what that means for the actual solution is the following, namely that along curves f with lambda being dx dt along f being a, well, what does it mean? It means that the solution is constant. So along those curves, the solution is constant. There is no derivative along that curve. And of course, that means nothing else that lambda is a characteristic. And it turns out that lambda is a real number because it's just a. And a, well, we have not written it, but we have assumed that this is a real quantity. So it's a real characteristic. And of course, that means in the classification that we did yesterday, that this is a hyperbolic problem. And of course, that's exactly what we kind of started off with. We wanted to describe hyperbolic problems. Okay. But now, of course, we can also think, so now we have identified how the solution would look like, and also that the type is hyperbolic, but we can also draw how the solution would evolve in the domain, kind of to better understand how a solution to an advection equation would look like. And what I typically do in order to illustrate that is I draw a so-called space-time diagram. Space-time diagram in a sense that I have the x-axis in the horizontal direction and the time direction in the vertical direction. And then what I look at is at time, let's say time 0, I plot here inside this diagram my initial condition, which I can assume to be 2 humps here. So that would be my solution u at time 0. Now what I would like to do is I would like to draw the same solution but at a later time, so t1 for instance. So if this is t0, I will go to t1, and of course there I would also like to draw it in this space-time diagram. Now, how would this solution look like? Well, we have just discussed that the main idea of the advection equation is that along curves f with this specific slope, the solution is constant. So that means I can actually go in and draw lines with this slope dx dt being a. And of course, this would then be, kind of slopes like this in the domain. So these green lines, they would correspond to lines with slope lambda. So these are the characteristics. And now we said that the solution is constant along the characteristics. So that means that maybe my solution would, just move like that in space from left to right with a certain speed, and this speed is exactly corresponding to the slope lambda of my characteristics. Of course, that means that I can also write my solution in closed form, namely that u at x and t, well, would essentially just correspond to a movement of my initial condition. So in this case, it would be u at x minus at, comma 0. Here we have this convection speed included in the argument. Or if I have an initial condition given at u0, at time 0, it would be x minus at of this initial condition. So the solution of the advection equation is nothing more than an advection of the initial data with speed a. And that, of course, the convection is along the characteristics. And in some sense, this is really what hyperbolic problems are all about. It is identifying characteristics along which information is being propagated. Of course, it's not always as simple as in this linear case, because the speed, so this a, because this speed that we have, this a here, may be a nonlinear function. It may depend on the solution itself, as for instance in Navier-Stokes or the Burgers equation that we will discuss later on. But the basic idea is always the same. You have information that is propagating along characteristics, it's advecting along characteristics. And that's exactly the idea of hyperbolic problems. Now, once we have understood this propagation property, I guess the next question is, well, we still need to make sure that our problem is well posed. And when we talk about well posedness, we need to think about boundary and initial conditions to make sure that we have posed the right conditions at the right place. And now that we know how the solution is composed of, or how information is propagating, we can perhaps also get an idea of where and how we should set boundary and initial conditions. Again, just think of a space-time diagram, and I was saying that we have characteristics, so maybe information propagates like that. If we now assume that we have a domain which goes from, let's say, x1 to x2, and initial conditions at t0, so we have kind of truncated the domain in this way. And we have an advection equation inside that domain, which has these propagation properties that I was just mentioning. Then the question is, okay, where do we actually need to have boundary and initial conditions? Well, as I was saying, we have information propagating along those characteristics, kind of in the way like this. And of course, now it becomes clear, if you want to have the information at those places where it actually enters into the domain, then we need to specify initial conditions and boundary conditions at these positions that I just indicated here with a bigger dot. However, at these positions, essentially when a characteristic hits an outflow, or goes into the boundary of the domain, that's the place where the information is actually just flowing out. There's nothing coming back in, just from the solution that we discussed. Which then, of course, also means that at those places, we're not supposed to prescribe boundary conditions. So that means, so if I just summarize that with a sentence, so to achieve well-posedness, it means that we need to prescribe conditions at the boundaries. We need to prescribe conditions at the boundaries, according to the number of ingoing characteristics. So that means if I have one ingoing characteristics, I need to specify one boundary condition. If I have one outgoing boundary condition, one outgoing characteristics, I need to specify 0 boundary conditions, because the information is just leaving the domain. Okay, so this was about let's say initial conditions and boundary conditions, how this works. There's another interesting aspect for hyperbolic problems, which I would also like to very briefly mention, and that is kind of the concept of where information comes from and where information is going to. And also for that, I would like to draw yet another space-time diagram, and we consider here a point P, X, and T. What we look at here is now a system, a hyperbolic system with 2 characteristics per point. So that means we have, let's say, 2 variables. That could be a U vector which is composed of U and V. So it's a vector. Remember, for the advection equation up here, we just looked at a scalar U. And of course, then the result was that we had one characteristic. But we can do that also with two variables, so a vector equation, and then we just get the two characteristics in the end. Two specific eigenvalues lambda or speeds lambda, which gives me then two different characteristics. Now, if I just assume, and I just sketch that one characteristic maybe looks like this. So this is, let's say, lambda 1, and the other one kind of looks like this. This would be the second characteristic, lambda 2. Now, what you can see from this is that it's actually quite interesting to understand that the region the solution of the point P is dependent on is only this hatched area. Information from any point outside of this hatched area will never be able to reach the location of point P. So that means the solution in point P is impossibly dependent on anything outside of this region. Because just from physical or let's say mathematical reasons, the information will never reach to the point P. Therefore, we typically call this region down here the so-called region of dependence. So we know that P, the solution in P, cannot depend on anything outside of this region. So, I mean, I can draw a characteristic here. Maybe that's then, the other characteristic look like this. So that means that the information will travel away from it. In a similar way, you can also study what region in the domain is affected by the point P. So imagine that you go in and you kind of hit the flow, or you change the flow in this point P, and then you can wonder what region of the domain is actually feeling the fact that you have affected the flow. And of course, in a similar way, this would then be the region between the two characteristics. And this we can call the zone of influence of point number P. And also, this is very specific to hyperbolic problems, because in the context of elliptic problems, well, we can maybe just make a note to that when talking about elliptic problems. Well, so compare elliptic problems. Well, remember we had this domain here, and we were talking about a point of x and y inside this domain. If you now think, what is the zone of influence and what is the zone of dependence in an elliptic problem? Well, what we said yesterday, everything depends on everything. So that means if I change the solution in point P, directly the solution everywhere in the domain will change, because it all depends on that solution. Similarly, if I change in another point Q here something, I put I hit the flow there, I know that also the point P will be affected. So in the case of elliptic problems, we have kind of understood that the zone of dependence is the same as the region of influence. And it would essentially cover the whole domain. And this, I think, just conceptually, and I can maybe do it like this in the same color, so that you directly see that the two regions in the elliptic problem are the same, whereas in the hyperbolic problem, these two regions are separated. And I guess this kind of in an intuitive way explains the big differences between elliptic and hyperbolic problems. And of course, now why are we talking about this? Well, I guess, of course, it makes it clear that numerical schemes adapted for these two problems need to be different because they have a completely different way of how the solution is composed of, and kind of what the influences it needs to take care of. Okay, good. So this was what I wanted to say about hyperbolic problems. For now, we will of course get back to that later on in the course, but as an introduction, this is what I wanted to tell you. Are there any questions about the hyperbolic problems? If not, then we continue to the next topic, and of course that's kind of obvious that now we will talk about parabolic problems. And in some way you can view parabolic equations to lie somewhere in between hyperbolic and elliptic problems, and the typical processes that are described with parabolic equations are, I think we can summarize it with this: it's equilibrating processes. It is typically processes that have smoothing properties and it's typically time-dependent properties. And I guess the typical example would be the heat equation. The heat equation or a diffusion equation. These are typical examples of parabolic equations. As we will see later on, also the incompressible Navier-Stokes equations, they're formally parabolic equations. But as I said earlier, you can also identify more hyperbolic and more elliptic parts of the equations. To illustrate in just a sketch, if I have x here and I have the solution u here, what is meant with this smoothing properties or diffusion properties, if I start at time 0 with kind of a solution that looks like this, kind of a sharp peak, what then happens when I subject this to a parabolic type or a diffusion type of equation? It will mean that kind of this hump here will kind of smoothen out over time. It will diffuse away. So this can be at T1 being larger than T0. Let's do this. And the equation now, if I'm just assuming that this was the heat equation, could be something like that: U times T squared U dx squared. Okay. Yeah. Let's maybe just start with this diffusion equation and try to formally calculate the eigenvalues and eigenvectors, just to kind of understand whether a heat equation is in fact a hyperbolic problem or not. So let's take the heat equation. Du dt is nu times t squared u dx squared. And now we would like to determine the type of this equation. As I was saying, most probably it will be parabolic. Everything else would be a surprise. But of course, we still need to be able to formally show it using the technique that we discussed yesterday. Now, if we want to do that, we again need to realize, as in the example of the Prandtl-Glauert equation yesterday, that we have a problem, namely that this is a second-order equation, but what we actually need is a first-order equation to use the method from yesterday. So we need to rewrite as first-order partial differential equation. And of course, we do the same trick. We kind of introduce an intermediate variable which has a first derivative, and then we take a second derivative in the second equation. So I do that very quickly. It's not very difficult. So we do it like this. So we rewrite it here with a first derivative. So I introduce a new variable v, which is defined as being the first derivative of u. Of course, now you see if I put this v in here, then I get the second derivative back. Okay, once we have done it in this way, we can go into the formalism that we had lost from yesterday. So I define this u vector to be u and v. My A matrix now becomes 1, 0, 0, 0. That's all the t derivatives collected here. The B matrix is all the x derivatives. So we have 0, minus, nu, 1, and 0. Essentially, I mean, this term and this term. And then the inhomogeneity would be 0 and v. That's essentially the right-hand side. And what we now need to do is to calculate eigenvalues for this generalized eigenvalue problem. B times A is lambda A. And then we need to look at the type and all of that. And if I do that, again, I'm not doing it here, or I'm not calculating it here, but of course you can easily do that. What I get is lambda, which will be dx over dt, will be infinity, and the corresponding eigenvector would be 0 and 1. Now, of course, that's a bit funny here that I write lambda as being infinity. Of course, it just means that dx over dt is infinity. If I would now write dt over dx, so if I had kind of switched over everything, this would be 0. So that's maybe easier to understand. But now I'm doing with dx over dt, so I get infinity. But what this now means, and I guess that's the important aspect, is that, well, first of all, we have real eigenvalues. I mean, 0 or infinity is a real number. There's no complex, no imaginary part associated to that. But at the same time, I see that I get 2 times the same eigenvector. So I have a double eigenvector, which clearly makes them linearly dependent. I mean, it's the same. And of course, that means in the end that we are in a parabolic situation because my eigenvectors are not linearly independent. So write that. Eigenvectors not linearly independent. And of course, that means as a consequence that the heat equation is parabolic according to the definition that we had earlier. Okay, so if you now try to make a sketch of how the information propagates also in a parabolic case, we do our typical kind of space-time diagrams, but now for the parabolic equation. So you have x and t, and we consider here a domain like this. So we have two walls on the side, and then of course we also have an initial condition. So we can say that these are the boundary conditions. This would be the initial conditions. And then I put in my point P as a function of x and time. Now, maybe the first question that one can have here is, okay, how do the characteristics look like? And it turns out, if we just look here, so dx over dt is infinity. So that means that the characteristics would look like this, like a horizontal line. So this would be the characteristics in this case. And of course, that's exactly in the same way as we also discussed with the Prandtl-Glauert case. Because if you just think of the transition from hyperbolic to parabolic, the hyperbolic case up here, well, we had it in this way, that it kind of formed a cone in, or a triangle in 2D, or a cone in 3D. And then if you think of that, you start to decrease the speed of the characteristics, it would just mean that these, it's difficult to show, but that these two sides would go down more and more up to the point that these lines would become horizontal. And of course, that's exactly the limit, because you cannot have characteristics that go backwards. That would not make sense from a causality point of view in physics. Yeah. So that means this is the direction of how the characteristics look like. And now we can also go and think further. Okay, what is now the region of dependence, and what is the zone of influence? And I think also that is kind of interesting to see. So if we do in red first the region of dependence, it turns out that the solution in P essentially depends on exactly what is lying around the what is lying along the characteristics. So that means that this would also be the region of dependence. At the same time, the zone of influence, so what can be influenced by changing, point P or hitting point P, it would actually be everything that is ahead in time of the point P. So this is then the zone of influence. Of course, if I'm writing it here as a time-dependent problem, it kind of makes sense that if I disturb the flow at time t, it cannot affect what has happened before. So it's time less than t. So down here. But of course, if I would formulate it as a problem that is parabolic in space, kind of this assumption is not directly as clear. But of course, it holds in exactly the same way. Now, the next question now is where to specify boundary conditions and initial conditions. And I guess also that it's more or less already shown here. I need to have conditions where my characteristics go into the domain, and I guess this would be on the boundaries and at the initial time. So we have initial conditions and boundary conditions. Let's say on the sides, and at time t being 0. What I do not need to specify, and it would make my problem to be ill-defined, I'm not allowed to specify boundary conditions up here at time t1, which is larger than the current time. This I'm not allowed to do. Okay, so this was parabolic problems. Also parabolic problems, of course, we'll go and get back to, particularly and also in connection with the Navier-Stokes equations. Okay, do you have any questions for these different types? If not, then I would like to continue with the second part, and that would be part B, and that is finite differences. So what we have done so far is well, we have discussed equations and their type. I guess in the table in the yesterday, very much in the beginning, these were kind of the first steps when we talk about the mathematical modeling and choosing a right discretization for that. What we now do is we actually try to reformulate. So in this chapter with the finite differences, we try to reformulate partial derivatives in a way that the computer can actually understand it and calculate a suitable solution. So that's essentially the basic idea of this chapter. So the idea is that that the dependent variables, so in that sense, u as a function of x and t, are considered to exist on discrete grid points only. So we go from a continuous space into a discrete space. And then the second step would be to approximate derivatives with differences. And if that means, kind of formally speaking, that we go from a continuous representation into discrete representation, and I go into an algebraic representation of the partial differential equation. So I'm not having a differential equation anymore, but I have a difference equation, an algebraic equation, which I can solve as a system of equations. Now, having said this, I mean, I'm talking about grid points and all of that. So that means I actually need to introduce a grid in some way. So maybe something like that. And of course, there's a number of metrics that I can talk about here. So I can have an x direction, I can have a y direction, and then I need to have indices. And I typically take the indices I and j, whereas the I index goes into the x direction and the j index goes into the vertical direction. So for instance, if I can call this point to be located at coordinates or indices I and j, then of course it would be that this point up here would be at I and j plus 1, and this guy would be at I plus 1, comma j. At the same time, I introduce a grid spacing, which I can call delta x, and this would then be delta y. This could be equidistant or not, but in the equidistant case, we can then say that delta x would be Lx divided by the number of grid points minus 1 in that direction, if we think of two solid boundaries. And in the same way, delta y, so the grid spacing in y would be Ly divided by ny minus 1. If nx and well, you can write it down. So Lx and Ly would be the domain size, so the size between the two walls, let's say, and nx and ny would be the number of grid points in the respective directions. So in the end, what I do, I come up with what we call a grid function uij, which can be viewed as an approximation of u that lives at xi and yj. That's essentially what I would like to do. And before we go to the break, there's a little bit of notation that we will use later on, or many people use. So if I have my grid function written in this way, so u, j, and n, this would typically mean that the subscript is reserved for spatial discretization. So this would kind of be xj course, I can do it also with two different directions. And superscripts, so the stuff up here, that would correspond to a temporal discretization. So time level n or time level n plus 1. So that's kind of the important thing. Superscripts, they refer to time, and subscripts, they refer to space. Okay, with this, I guess we can stop for the first hour, and we will then continue in 15 minutes. So I will pause my recording. Okay, very good. So now welcome back to the second hour. So what we have done just before the break was to define the grid function. So meaning that we have discretized the domain. So we have put a grid, and we have written our grid function. So meaning that we have gone from a continuous representation into a discrete representation where the solution only lives at these individual grid points at I and j. And now the next step would be to define derivative operators that can actually calculate derivatives on these discrete points. And that would now be the next chapter. I think 1.1, it would be derivation of finite difference schemes. And I guess it's quite straightforward what we do here, but I still think it's important to go through that so that we have kind of formally seen it. Yeah, so what do? Well, we essentially use Taylor expansions. That's always, whenever you do finite differences, Taylor expansions is essentially the tool that you use all the time. And well, a Taylor expansion of u at x plus delta x based on ux is simply that ux plus delta x is u at x plus delta x times u dx at position x plus delta x squared divided by 2, there's a faculty of that, times d squared u dx squared, again evaluated at x, plus delta x to the power of 3 divided by 3 faculty d squared u d to the 3 u dx to the 3 evaluated at x, and so on. So this is nothing else than Taylor expansion. Okay. So now, how can we use this as to define a derivative? Well, what we see here is that there is actually a derivative du dx at position x appearing right in this equation. So we can just take that and write that on the left side. So we have du dx at x, and now we can just put everything else on the other side, and we get u at x plus delta x minus u of x divided by delta x. And then, so that's this term and this term. And then, of course, we have all these other terms as well, which we can write here at the end. So that will give me delta x times 1/2 d squared u dx squared at x plus delta x 2 divided by 3. That's 6, of course. Sorry. 6 times d3u dx 3 at x, and so on. And of course, now you see that I have an approximation for my derivative if I'm just taking kind of the first bit here. Of course, this is an approximation because I have these error terms here, but these are what we call of higher order. So we can say that all this stuff is of order delta x. So the leading term in this error term is of order delta x. And what we have achieved here is a finite difference approximation, which we can call d plus as an operator operating on our grid function ui. I'll later explain what I mean with or why I call it D plus. Let's just make a very quick sketch about that. Also, this is something that you have most certainly seen before, but still I think it's important. So if we have a curve here, we have grid points, something like that. That's xi, that's xi plus 1, xi plus 2, xi minus 1. So we have, so we have this point, this point, this point, and this point. And now what we have done here is this D plus approximation. So essentially we have put in a straight line, and we approximate the derivative in this point by the slope of this red line. So this would now be the D plus operator. Now, the reason why there is D plus, that means also that there's maybe a D minus. And of course, the idea now would be I could approximate this derivative also by putting in a straight line like this and taking the slope of this, and that would be the D minus operator, where essentially I take the difference between xi and x minus 1, that's for D minus, and for D plus I take the difference between those 2 points. And as I will show later, but I can already now draw it into the figure, a third way, which in some sense is even a better case, would be to take the difference between this point and this point and and put in a line, and this would then be finite differences D0, as I will tell you later. So that's kind of the average between D plus and D minus. But this is essentially the idea of finite differences. I put in this case linear, so lines into between the points, and I approximate the derivative with a linear line. And of course, you can do more. And the homework number, I think homework number 2 has one example where you should calculate a derivative based on 4 points, where the whole idea is just to combine Taylor expansions in the best possible way. Okay, so yeah, that's kind of it about the finite differences. There's of course a few more comments that I can make. So first of all, I can tell you very quickly that in what way we can write those also, this operator that I've introduced here, also in terms of matrices, which may at times have some advantages if you just want to test a few things. We can write as a vector matrix. Multiplication. There the idea would be that essentially I just take this and write it as matrices and vectors. So I define my vector of the unknowns, so they're my grid points essentially. That would be ui minus 1, ui plus 1, and so on. And then I can define my d plus. I should of course make it the other way around, dn plus matrix, so that's my derivative matrix, which encapsulates exactly this operation, so taking the difference between these 2 grid points into a matrix form. And that would then become something like this, 1 over delta x, and the matrix now would be, it has minus 1s on the diagonal, and on the super diagonal, it would have values of 1. Something like this. And the rest is all zeros. And if you now think of calculating the derivative, so we can formally write that un prime as the derivative would be d plus n matrix multiplied with the vector un. Maybe one thing I have not mentioned, but I use here the letter n to kind of indicate that we're not in the continuous space anymore, but that we're approximating a numerical solution. Okay, so this in this way I can simply create the matrix which computes my derivative. And of course, that's also not surprising when you just think of it, that the derivative is a linear operation, and a matrix vector multiplication, of course, is kind of the quintessential way of doing linear operations on a vector. And of course, now remembering the discussion that we just had in the break, here, of course, it needs to be an approximative sign because I'm doing second order or first order finite differences. So this is an approximation to the derivative. Okay. Yeah, I guess there's not much more to say here. Maybe I can just introduce also the well, we have now this. We had the d plus derivative, which we called the forward or right-sided finite differences of first order. Of first order is we will define that later on, but the idea of first order is that the error term, so the first term that is not correct, is of first order. So this was the d plus derivative, but at the same time I can define the d minus, which we have seen here in the sketch as well. And there the idea is this would be backward or left-sided finite differences of first order. And of course, for the d minus operator, so d minus applied to ui would then be ui minus 1 divided by delta x, and this is u prime at xi plus an error term of first order. And then d0, that would be the third option, and this would now be central finite differences. Central finite differences. And it turns out, and we will calculate that later on as well, these are actually of second order. And also this I can quickly write down. So d0 applied to ui would then be ui plus 1 minus ui minus 1 divided by 2 delta x, and that would be an approximation of the derivative, but then the error term here would be delta x to the power of 2. Okay. Yeah, as I said, it's probably nothing new to most of you, but it's still good to kind of recapitulate all these things. The whole trick is to do Taylor expansion. That's really what this is all about. Okay, now maybe the next topic is already a little bit new to some of you, because we can formalize all of this and introduce the concept of a truncation error. Truncation error is essentially the error that I commit by having a finite grid spacing. So that's the error that I do when I go from the continuous representation into the discrete representation. And of course, this truncation error that appears exactly here when I do finite differences, but you can also view it as a much more general concept when I go from my continuous flow field or representation into the discrete one. So truncation error is always the error that I do due to finite grid spacing. And of course, what we want to do now is we want to formally calculate the truncation error of finite difference operators. But as I said, we can do that also later on for whole equations, and we will use that concept quite a bit. But let's now just do an example, and we apply it to second order or to central finite differences. I just do the example. We look at the D0 operator essentially. Well, so what we want to do is we would like to calculate the truncation error, and the truncation error is defined as the difference between the exact solution and the discrete solution. Or actually, we can write it like this, as the discrete solution minus the exact solution. So if I do that for D0, it would be D0 applied to UI minus the exact derivative evaluated at the point xi. That is what we would define our truncation error. Okay, so how would we calculate this now? Well, I guess it's again we just use Taylor expansion as we have done before. But the idea is if we have here the definition of our D0 operator, we just put Taylor expansions into UI plus 1 and UI minus 1, and then we subtract the exact derivative. So essentially we write using Taylor expansions. So Taylor expansion we do for x plus u of x plus delta x. That would be u of x plus delta x of du dx plus delta x squared divided by 2 of d squared u dx squared, and so on. And as you see here, we also need to have ui minus 1. That corresponds to ux minus delta x. And of course, that would be kind of the same expression, just with minus signs for the odd derivatives. Something like this. Okay, actually, I should be careful here. I should also take with us the third derivative, because that's what we need afterwards. So, and then if I do the third derivative also here, that's minus delta x to the power of 3, 6 d3u dx 3, and so on. Okay. Yeah, so now I just put in my I put in the Taylor expansion in this expression for the truncation error. So we have ux plus delta x minus u of x minus delta x divided by 2 delta x, and we need to subtract the exact derivative, so du dx evaluated at xi. And if I do that calculation, which is not very difficult really, it's just taking this expression, putting it here, this expression, and putting it here, and then essentially see what terms all disappear. And the result, if I do that, will be 1/6 of delta x squared times d3u dx to the power of 3 evaluated at xi, plus some higher order terms. Now, how does this go away? Okay. And of course, what I see here is that the leading error term, so the term with the lowest exponent in terms of the grid spacing, is actually delta x squared. So I would say that this term would be of order delta x squared. And what we have now shown here is that the truncation error, so the error that I commit by going from continuous to discrete, is of this form here. So it has a term 1/6 delta x squared times the third derivative plus higher order terms. So it means in the end it is of order delta x squared. And there's two important observations that I can make. First observation is that, as I just said, the error is of order delta x squared. And therefore, we call this scheme to be of second order, because the error is, the first error term is of second order. So that's maybe one observation. And the other observation, which is even more important later on when we talk about that, is that the error actually goes to 0 for delta x going to 0 as well. So the smaller delta x is, the smaller the error becomes. And I guess that's an important statement to make, because it means that the finer my grid is, the better my approximation, the lower the order is. And in the limit of zero grid spacing, I will have 0 error. And of course, that's exactly what I would like to have. Okay. Yeah. This is all I wanted to say about the kind of the classical derivation of finite difference schemes. It's really all about Taylor expansions. Taylor expansions backwards and forwards, and then you can derive all these different things. And the rule of thumb is that if you have, or I mean, rule of thumb is maybe the wrong word, but the more points and the further away, so the more points that you have in your approximation for the finite difference scheme, the better the quality will be, or the higher the order of the finite difference scheme is. So in this case, we have typically used 2 points, which means that we have put in a line, which gives us a first order scheme. But if you add 3 points or 4 points, then you can get a better quality of the derivative. I can just show you that as a quick example, or a quick demonstration about what I just said. So I don't know. Do you see now this? Do you see my text on the screen? I have opened the PDF. Can you see that?
No.
No. But then I'm just sharing the. Wait, I need to do like this. So let me do like this. Okay, now you see it.
Yes.
Okay, very good. So this is a document that is also on the home page, but it's also in the lecture notes, where I just collected a number of different finite difference schemes. All of them derived in exactly the same way as what we just done here. And as you can see here, there's a number of different ways of expressing first order derivatives. So the ones that we have just looked at are the left-sided finite differences, right-sided one, so left-sided one first order, right-sided one's first order. But then you also can increase the order, so increase the accuracy by essentially including another point, so a third point. So it's not just ui and ui minus 1. You can also include them ui minus 1, and ui minus 2 for calculating the derivative. And what you see is then that the leading error term goes from delta x to delta x squared. The same thing, of course, you can do on the right side as well, and in the central way you can do exactly the same. So this is the central scheme D0 that we talked about. But if you also include I plus 2 and I minus 2, then you get a scheme which is even of fourth order. But again, the construction of all of this is exactly in the same way that we just did. You just do Taylor expansions, and you make sure that in the final sum, all the terms of low error order will cancel each other and go away. You can derive formulas not only for first derivatives, you can also do it for directly for second derivatives, as shown here. And then you get these type of schemes, which we will also use later in the course when we approximate diffusive problems, where of course you have a second derivative. Same idea here, same steps. And you can do it for third order derivatives and fourth order derivatives. Okay, good. Then, yeah, I guess this is what I wanted to tell you about kind of the classical derivation of finite differences schemes. There's one more point that I would like to make here, and we will also look at that a number of times later on in the course. That is actually an alternative way of assessing the quality of a finite difference scheme. And that is the concept of a modified wave number. And as I said, this is just another way of understanding what effect it has to go from the continuous representation to the discrete representation. And what we have just done, we have done Taylor expansion just before. And what we have gotten out from that, we got the order of the scheme. And that gave us an idea of the truncation error. And in some sense, we can say that this is a local analysis of the error, because we know now the error in terms of the local grid spacing. And so local analysis in terms of grid spacing. But what I would like to show you now with the modified wave number is another way of looking at it. Namely, we would like to look at the effect in frequency space. So to what extent is the frequency content of a specific solution affected by doing a derivative with finite differences? So we can say that this is then a global analysis in terms of wave number or frequency of the solution. In order to do that, and I guess you already kind of suspect it, we probably need to go into Fourier space. So we need to do a Fourier transform to go from physical space to spectral space. So therefore, what we do now is we consider a function, and to make everything a little bit simpler, we consider it to be periodic on a domain which has a length of 2 pi. It doesn't need to be, of course, periodic with 2 pi. It just makes it simpler, because then kind of the fundamental wave numbers will disappear. So let's consider something which is periodic on 2 pi, and also because we know that the derivative is a linear operation, it is actually sufficient to just look at one Fourier mode at a time. And then we can compose our complete solution as a superposition, a linear superposition of all these individual Fourier modes. So due to linearity, let's just consider one Fourier mode at a time. And one Fourier mode periodic on 2 pi would be something like this. U of x could be e to the I kx. And this k here would be integer numbers. So it could be 0, it could be 1, and so on. And of course, this is what we would call the wave number. Now, I know that most of you have discussed this complex representation of exponentials before, but I know from previous years that it may be kind of good to just repeat that for everybody what is kind of meant with this representation. So I'm just doing that very quickly. So if you have e to the I phi, so an exponential of a complex of an imaginary number, then this can be also written with the I guess it's called the Euler formulas as cosine of phi plus I sine of phi. And now for the example above here, I have used that phi is actually k times x. I mean, this and this to be the same. Phi would be k times x. Now I can just draw for you how individual Fourier modes actually would look like. So if I start with k being 0, that of course means that e to the I kx would simply be unity everywhere because it's e to the 0. And if I just want to draw that in a, if I draw that in a graph, so if I have x here, maybe 2 pi, and this would be 0, and actually I should make it like this. So x 2 pi here it would be 0, and here it goes from minus 1 to 1. Then of course this first Fourier mode would essentially just be a constant from 0 to 2 pi. So this would be k, the Fourier mode for k being 0. Of course, what I draw here, that's the real part of this e to the ikx. Now, if I go to k being 1, so that would now be a wave number of 1, then the complex exponential would become e to the ix, so in case 1, and with the help of the Euler formulas, this would be cosine of x plus I sine of x. And if I'm plotting here now the real part, I would just plot a cosine, essentially. And if I try now to plot the cosine, this would be something like this. So this would be k being 1. So that is a wave which has exactly one crest over the domain of 2 pi. And that, of course, means that's wave number 1. One crest, wave number 1. And then I can just continue. So k being 2, it would be e to the 2x here. And if I write that out with the Euler formulas, it will again be cosine of 2x plus I sine of 2x. And if I plot that, that would then be wave number 2, so it would be 2 crests. Now let me try to plot this. Something like that. And so on. So a wave number of 3 would then be 3 crests, a wave number of 4 would be 4 crests, and so on. But the basic idea is that the higher k is, the more crests I have in this domain. So that means that the frequency of the oscillations will increase. I get smaller and smaller scales in the domain. So that's the whole idea of what I would like to do here. I would use, or I would like to see the effect that the finite difference scheme has on waves of different sizes. So as a function of the wave number, I would like to see what happens. Okay, so let's now do this this calculation. It's actually quite straightforward, but still I like what comes out. So if we first start with the exact derivative in Fourier space of this Fourier mode that I had, ux is e to the ikx. So what is the exact derivative? Well, it's well, I can write it like this. So u of x being e to the I kx. Yeah, what is the exact derivative with respect to x? Well, it's just deriving this with respect to x. It's an exponential, so it will be the same, and then we have the chain rule. So the exact derivative would be e to the ik e to the I kx. As simple as that. And this would be the exact derivative. So in the best of worlds, if I had a perfect scheme, a perfect finite difference scheme, this would be the derivative that the scheme would give me. But unfortunately, this is not the case. So using a finite difference scheme, now the idea is that we should look for a similar relation as the one that I have just gotten for the exact solution. So what I mean with that is that I would like to write my numerical derivative in a similar way, ik e to the I kx. But now I need to understand that this is an approximation. This finite difference scheme is not exact. So that means that probably there will be a prefactor here which is different. So therefore I'm writing here a tilde on top of the k. Maybe I can write the whole k here in red. So that I understand that this k tilde is actually not the exact wave number that I had from above. It's not the exact k, but it's something that is modified. And of course, that's exactly the modified wave number. So now the task is to understand how is this k modified by the finite difference scheme, modified from away from the exact wave number, which would just be k, but to what extent does the finite difference scheme affect that? And of course, now I can write an expression for this k tilde as a function of k, which would be simply u prime of x numerical divided by e to the I e to the I kx, something like that. So this is the definition of the modified wave number. Now, how can we use that, or what happens really? So just write down, let me write down a short sentence. So the exact modified wave number, well, obviously then it would not be modified, is k tilde being k. But as we will see, it will not be like that for a scheme. Therefore, any difference or a departure, let's say, any departure from that is a measure of the accuracy of the finite difference scheme. As a function, that's the important thing, as a function of the wave number k. So now we have a measure of the accuracy of the finite difference scheme as a function of k. So that means depending on whether we look at small or large scale oscillations in the flow. And that, of course, is very different to what we got with the Taylor expansion, with the truncation error, where we just got one number, one order, which is valid for everything. Now we can say, this scheme is very good for large scales, but very bad for small scales, and so on. So that's the interesting bit, that we got this dependency on the wave number into our consideration. Now, let me just conclude this with a simple example, and we look again at the central finite difference scheme of second order, so the D0 D0 operator. And this was then such that the numerical derivative is something like this: ux plus delta x minus u of x minus delta x, and this divided by 2 delta x. Okay, now I need to do a I need to introduce my Fourier mode that I had from above. There it is. So this Fourier mode I just need to introduce in my finite difference formula. So that means 1 over 2 delta x of e to the I k x plus delta x minus e to the I k x minus delta x. Okay, so now we see we have a difference of complex exponentials, and again with the help of the Euler formulas, we can actually go from this back to sines and cosines. I mean, just where did we have it? With essentially these type of formulas, we can go back into a representation with sines and cosines, and in this case, it will turn out that a sine is enough to represent this difference. So what we get, and this is still analytically correct, I get I times sine of k delta x divided by delta x times e to the I k delta x, I k x. And now, this should be, as I was writing above here, this should be kind of the same as the similar relation as we have for the exact derivative. So this should be I times k tilde times e to the I k x. And of course, with this, we can directly extract what this k tilde as a function of k really is. And this is essentially this term here. So we have sine of k delta x divided by delta x. And this now is my modified wave number. Yes, it's easiest if you just draw this. And what I draw here is k times delta x on this axis and k tilde times delta x. The reason why I'm using here a multiplication with delta x is to make sure that I get something which is dimensionless, because k, the wave number, has the unit of 1 over length, and the delta x obviously has the unit of a length. So this will be dimensionless, which also means that this plot will go from 0 to pi, if you think of how many modes you will have. Now, the exact modified wave number would be just a straight line. So this would be k tilde being k. That's the exact thing. That's essentially, if you had a perfect scheme, it would look like this. But now, by looking at what we have gotten for the central scheme, k tilde times delta x is just a sine. Well, how does a sine from 0 to pi look like? Well, that's something like this. And now I guess we can see what the problem is. We can see that in this region here, so close to, or in the region where we have low wave numbers, so large waves, we actually have a good approximation. Good approximation for low wave numbers. Because the red and the green line, so the green line, which is the modified wave number, is very close to the red one, which is the exact one. However, in this region, we see a large difference between the red and the green line. And of course, that indicates that this is a bad approximation. A bad approximation for high wave numbers. And of course, now the question is, in what way is it bad? Well, it's bad in a multiplicative sense, because here you can see that, where is it here? Here you can see that the numerical derivative is the original function multiplied by the modified wave number. And here we multiply with something that is actually much lower in value. It kind of goes back to 0. So essentially what this means in a physical understanding, well, it means that we have introduced some severe damping of the derivatives at high wave numbers. In the extreme case, the highest derivative that we can represent is multiplied with a 0. So that means we actually don't get anything as a derivative. Okay, so this is we will spend maybe 5 more minutes next time on discussing that plot. But for now, this is the conclusion, that we have now seen this difference between the exact and the modified wave number. With this, I would like to stop for today and wish you a nice day. And I guess we continue already tomorrow with another 2 hours, where we then continue with finite differences, but this time in time, so temporal derivatives. Okay, so I'll stop the recording.